Welcome to the next module. In this module, we will be studying about influence of ozone and UV radiation in the Arctic. So here is few images which are given. The locations are, if it is a stratosphere, the function of ozone is it absorbs the harmful UV radiation, and the impact is it protects the health and ecosystems. But the same ozone in the troposphere is a bad one. What it does is it actually forms from the reactions between pollutants and the sunlight. So this causes respiratory issues and it harms plants. So that means ozone has both good and bad aspect. So here is a few images taken from Antarctic region. So in September 1981, you see there is a very aquamarine like color is given here. And here you see a little bit blue color. This happens in September 1987, and in September 93 also the intensity of the blue increases, and in September 99 also it remains more or less the same. So this particular effect is called as ozone layer depletion. So this is given in the Dobson unit. We will be looking at what is a Dobson unit. So the blue color means the thickness of this layer is very less. So that is what here it is like 100 Dobson unit or very less amount is given here. In other words, what we can infer from this image is in the year 1999, we can see that the amount of ozone in the atmosphere had reduced drastically. So that is the inference. And in the Arctic, if you look at 2019, we do not have a blue color. Blue color means basically the amount of ozone is getting depleted. So here we have a pretty high amount of ozone in 2019 in the Arctic region. But in March 2020, there is a huge ozone hole which is starting to appear in the Arctic region. So how do we know all these things? Basically in 1913, the discovery of ozone layer was carried out by French physicists Charles Fabry and Henry Bunsen. Both of them mentioned about the ozone layer. They identified the presence of ozone in the stratosphere. Then in 1957, the International Geophysical Year, the worldwide network identified that ground-based ocean measurements stations were initiated to see what is happening in the ozone layer. And then in 1970s, discovery of ozone depleting substances were found. Molina and Sherwood Rowland had identified that. They studied the effect of chlorofluorocarbons on ozone depletion and predicted ozone layer damage. In 1975 publication of key research by Molina and Rowland, they showed that how CFCs release chlorine atoms that destroy ozone. The chemical reaction began that was shown here. In 1985, the discovery of the Antarctic ozone hole was carried out by British Antarctic Survey team, which included Joseph Farman. They first observed drastic ozone depletion over Antarctica, raising global awareness. Due to these changes, what had been happening is in 1987, the adoption of Montreal Protocol was initiated by the United Nations. So this is an international agreement to phase out ODS, ozone depleting substances, marking a significant step towards ozone protection efforts. In 1992, the assessment report on ozone depletion by UNEP highlighted the need for continued monitoring and protection of the ozone layer. In 2000, the ratification of the Kigali Amendment by the UN member states happened. Here the agreement to phase out hydrofluorocarbons, further protecting the ozone layer. And in 2016, signs of recovery of ozone layer had been reported by the scientific communities, especially NASA and NOAA. Their study showed that the ozone layer is beginning to heal due to global effort to reduce ozone depleting substances. So some of the historical ozone depleting events in the Arctic include, in 1980s, initial concern about the ozone depletion due to CFC was found. That means this is basically considered as the base unit or the pre-significant depletion level. Here 300 to 400 Dobson units are there. What is a Dobson unit we had mentioned earlier? It represents a layer of ozone that when compressed to standard atmospheric condition, that is at sea level, would have a thickness of 0.01 millimeter, that is 10 micrometer. That is what is called 1 Dobson unit. So here in 1980 we had around 300 to 400 Dobson unit, but in 2000 the minimum ozone levels recorded in the late March, which is around 250. There is a 30% reduction compared to the pre-1980 levels. In 2005, there is a significant ozone loss. The value reached approximately 220 Dobson unit, that is over 40% depletion in certain regions. And in 2011, the average ozone level observed was around 300 Dobson unit. So the continued monitoring shows there is a recovery. And in 2019, there was an unprecedented event where the value went to 200 Dobson unit. This affected the areas approximately 1 million square kilometers. In 2020, there is a recovery, and currently we see around 300 Dobson unit is there. There is an improvement in the ozone concentration. So what are ozone depletion episodes? The ozone layer is an invisible shield that exists 15 to 35 km above the Earth's surface. The ozone layer is basically protecting the Earth from biologically damaging ultraviolet radiation, heating the stratosphere, and also interacts with the terrestrial infrared radiation. The depletion of the stratospheric ozone layer has been the major environmental issue of the past decade, especially since the discovery of the Arctic zone by Altmans and Antarctic ozone hole by Farman. The Montreal Protocol on substances that deplete the ozone layer was signed in 1987 and was ratified 2 years later. So what is the mechanism of depletion? The ozone depleting substances release chlorine and bromine atoms when they break down in the stratosphere. The polar stratospheric clouds provide the surface for these reactions. These atoms, chlorine and bromine atoms, catalyze the breakdown of ozone into oxygen, significantly reducing ozone level. We had seen this in the halogen chemistry of Arctic region. We had seen many of these reactions. In the seasonal variability, of course, the ozone depletion does not occur throughout the year. The ozone depletion occurs particularly during the spring in the polar regions, notably over Antarctica, leading to the phenomenon known as ozone hole. What is the geographical impact? While most prominent in the polar region, of course this happens in both the Arctic and the Antarctic, but then ozone depletion also occurs in the mid-latitude, affecting broader areas. What is the effect? Mainly, the increased UV radiation due to ozone depletion can harm marine ecosystem, terrestrial plants and human health, leading to higher incidence of skin cancer and cataract. So what is the international response to reduce or mitigate this? The Montreal Protocol, adopted in 1987, is a key international treaty that aimed at phasing out various compounds which are ozone depleting substances, leading to a gradual recovery of ozone layer. That is like currently we do not use chlorofluorocarbons in the refrigerator. So that is one of the reason from the Montreal Protocol, people stopped using chlorofluorocarbons. Satellite observations and ground-based measurements are used to monitor the ozone levels and the extent of depletion. This helps in understanding and mitigating the issues. Ozone depletion interacts with climate change. This changes in temperature and weather pattern can influence the ozone dynamics. We will look at an important cycle called the Chapman cycle. This is used to explain how the ozone depletion actually takes place. The slow production and destruction of odd oxygen, that is OX is equal to ozone plus triplet atomic oxygen, along with fast interconversion of ozone and OP3. P3 is nothing but a term symbol for atomic oxygen in the triplet state within the OX family. This Chapman cycle is basically a oxygen only model. So the reactions are ozone formation is given, ozone destruction is also given. So this is what is called the overall Chapman cycle. In the first step, ozone formation happens, that is photodissociation of oxygen happens. UV radiation above 242 nanometers from the sun splits the molecular oxygen into individual oxygen atoms, that is oxygen radicals, like O2 plus UV light gives 2 oxygen dot. The step 2 is the formation of ozone. Free oxygen atoms can then rapidly react with this molecular oxygen to form ozone. So O dot plus O2 gives O3. And then the next event what happens is the ozone destruction. The photodissociation of the ozone happens here. The ozone can also absorb UV radiation and dissociate back into oxygen molecule and free oxygen atoms. And further reactions are the free oxygen atom can react with again ozone, leading to the further destruction of ozone. Even though ozone formation and ozone destruction happens, most of the time ozone destruction outweighs the ozone formation. So what are the limitations of this Chapman cycle? The main limitation include, here we only talk about the chemical sources as OX, oxygen species only, that is photolysis of oxygen, but does not include other major processes like loss of stratospheric oxygens via catalytic cycle that destroy the ozone through reactions involving heteroradical. The previous one what we had seen, halogen radicals and hydroxy radicals, all those reactions are not involved. And here are the reactions that are given. The halogen oxides, that bromine oxides and iodine oxides and chlorine oxides we had seen, that react with oxygen radical to give halogen radical and oxygen. This halogen radical reacts with ozone. This is what is the ozone destruction reaction, leading to the formation of oxygen. So the net reaction is oxygen radical reacting with ozone to give 2 oxygen molecules. In the lower stratosphere, bromine also contributes to ozone loss, but the Chapman cycle does not include bromine. Similarly, the oxygen radical increases with altitude. So does the production of ozone, that is also not captured. So how the ozone destruction happens specifically in the polar region? In the stratosphere, chlorine oxide can dimerize to form Cl2O2 molecule. When the sunlight returns in the spring, the Cl2O2 can be broken down by the ultraviolet radiation, releasing the ClOO peroxide radical and generating the reactive chlorine radical. So 2 radicals are produced. This is a very crucial one. This chlorine peroxide radical reacts with any substance to give chlorine radical and oxygen, and the substance is released. Then the chlorine radical again reacts with ozone, giving chlorine oxide and oxygen. This is the destruction of ozone happens at this stage. So the net reaction here again is 2 ozone giving 3 oxygen molecules. See, the chlorine radicals basically reacts with ozone to destroy it. Since the chlorine oxide is formed, this can further start the dimerization reaction. So this is like the catalytic cycle, and this keeps on happening. In other words, a small amount of chlorine oxide can destroy large amount of ozone. In the second catalytic cycle, the chlorine oxide can react with bromine oxide to give both chlorine and bromine radical. So instead of 1 bad person, now we have 2 bad persons. They each can now destroy ozone. That means double the amount of ozone can be destroyed because of these reactions. Then the concentration of chlorine oxide is very less outside the polar region. The chlorine oxide dimerization occurs only in the low temperature, that is the polar region. So these are all the 2 crucial factors, and because of this, the ozone layer depletion happens mainly in the polar region. So the amount of chlorine oxide during the polar spring is determined by heterogeneous reactions of inorganic chlorine species that we have seen how they are produced. These are occurring by on the surface of the polar stratospheric cloud particles, that is the place where the reactions actually take place. They also take place on the cloud sulfate aerosols and by the efficient removal of nitrite, denitrification by sedimentation of PSC particles. So these are all the ways by which the destruction in the polar region occurs. And what is the limitation means we do not have a full understanding of the kinetics of chlorine oxide dimer catalytic cycle. There may be few unidentified processes that may cause faster loss of chlorine oxide. What happens to Cl2O2 absorption cross section at wavelengths longer than 310 we are not aware of. There is possibly a pressure and temperature dependent formation of other Cl2O2 isomers which we do not know. Very fast and unidentified reaction involving ClO and Cl2O2 are unknown.